Welcome students. Today is the 15th lesson. Today I am going to tell you about the network analysis. Actually what happens in GPS, already we have seen that we will go for point positioning or baseline processing. Now after finding out the position of any point, we go for its accuracy testing, and then when we find that the point is accurate enough in position, then we go for baseline processing, and also we may find that the baseline achieved the accuracy which we are looking for the particular project. In spite of this, you may sometimes find that the mutual position of different points or different control points stations or the relative orientation of different baseline may not be as desired. So we need to go for network analysis to find out whether the mutual position of the control points are okay or not, and also sometimes we find that there are some blunders available in the observation which may, in spite of all the pre-processing and error correction, they may still be present inside the data. So we need to clean those blunders, and also sometimes the residual errors in the observations may be strong enough to disturb whole of our GPS positioning results. That means the accuracy achieved may not be of sufficient quality. So under these conditions we need to go for further analysis of the GPS data, that means further processing of the GPS data, that is done through network analysis. So in this class we will be going for network analysis of GPS surveying. Now discrepancy arises due to orientation, or that means the geometry may not be the geometry of the figure. Suppose I have 3 stations like this or 4 stations like this actually in the field, but after processing I may get the thing, I may get the location like this. Now actually this is we want, but we find like this. So this clearly says that the orientation of this is not as desired. So sometimes when it is the, suppose there are 4 stations, so we have a rectangle like this, but we may, if there is an error in this like this, now you can see this rectangle is well shaped, but this rectangle which we found is not of well shaped, that means geometry has been jeopardized. Sometimes the, you can see the area of this is more than the area of this, that means our desired the scale of the processed figure is less than the scale of the smaller scale, so its shape, its size is less. So discrepancies arising out of the scale. Then also sometime, now you can see here the geographical position of this is totally different from this. So scaling, then geospatial positioning, of the figure. So there may be discrepancy in these. So these discrepancies Now these discrepancies we do take care through network analysis or network adjustment. Now and usually these discrepancies arises out of two things. One is that blunders in the and residual errors. These are the these are the two factors, or these are the two because of these two presence in the observables that we may get these discrepancies. Now due to presence of blunders and residuals, sometimes the network which we will be getting through processing may not close, that is called misclosure. So and through network analysis we need to identify the blunder, and to remove it we need to identify and remove blunder from observables. We have to distribute or adjust residual errors among all the points or components of the network, and the output of the network analysis, will be correct position of control stations. Now by the word correct we have 2 points to be noted. One is that the locations are accurate, as well as its geospatial location. Geospatial location is as desired or in desired place. So the control station, the location of control station at the desired location in accurately we will be able to get through network analysis. So this is the objective of network analysis, that means we have to find out the very accurate location of the control stations as per their geospatial location, relative location, and this is being achieved through 3 stages of analysis, that is called, first is preliminary analysis. Preliminary analysis we have to do. Now during preliminary analysis we do find whether the baselines of the GPS data or observables available are worthy for network analysis or not. Now to do this thing there are 2 things we need to do, 2 operations we need to do. One is called connectivity test and the other is misclosure test or closure test. Now under connectivity test we see whether the stations, suppose I have 4 stations where the observations are taken. So suppose 1, 2, 3, 4. Now suppose I have 2 receiver, so I will take the observation between these 2 stations first, then I will take the receiver from here to here, so I will take the 2. Now you see the observation of 2 and 3 has common with this station. Now keeping 3 in its position, the receiver at 1 will be shifted here and we will take the observation here. Then the observation at 3 and 2 will be common. Now from 2 I may shift this instrument to 4, and if we take the observation between 3 and 4, then the observation at 4 and 3 will be common, and then the receiver from 3 to 1 I should bring. So the observation from 4 and 1 will be there. So in this case we will have the overlapping observations. So now all these baseline has been observed properly, but suppose I have if I take an observation 1 and 2, but then after taking 2 the receiver is coming to 3, so I have taken the observation 1 and 3, then if I shift the receiver from 1 to 4, then we will take the observation 3 to 4, and then if I shift the 3 to 1, this is the first shifting, this is the second shifting, this is the third shifting. So I will be taking this. Now if the observation is like this, now you can see there is no overlapping observation between 2 and 3. Now this is open. So if we have the observation like this, then the connectivity test will fail in this case. In this case connectivity test will pass, it will be fail. So if the connectivity test fails during our preliminary analysis, then we have to find out between which stations we have no observation, and we have to go back and we have to take observation between these two stations with some overlapping with other stations. So that is what is connectivity test, to see whether all the baseline has observations and some overlapping observation between two stations are not there or not. Then we have to go for misclosure test. Now as I told you that the observation in this case the connectivity test has passed. Now I have two triangle 1, 2, 3, you can say this is a closed triangle, and a triangle 1, 3, 4. Now if I take the change in and these coordinates are denoted by Cartesian coordinate x, y, z. Now the change in x coordinate from this point to this point, from this point to this point, and from this point to this point, the summation of that should be equal to 0. Summation of y equal to 0 and summation of z coordinate, change in z coordinate should be 0 in ideal situation. For now if this condition fulfills, that means our figure is closed, and if any one of this is not equal to 0, that means there is some error in closure. That is the misclosure test, and invariably all these will not be equal to 0, so there will be some misclosure. So what we should do, then we have to see whether the misclosure is within permissible limit or not. If it is within permissible limit, then we can go forward for our next step, or if it is not, then we have to go for further, again go to the field and take the observation, and we have to find out the locations, and we have to find out the coordinate of different stations, and we have to test it till it passes. So once preliminary analysis is successfully done for the network and its data, then we should go for next part, that is called adjustment. Now adjustment of network adjustment is also done in two steps. One is called minimally constrained adjustment and the other is called constrained adjustment. Now minimally constrained adjustment, actually in minimally constrained adjustment any one of these station, coordinate of any one of these station is considered to be fixed, and then we do find out the coordinate of others, and in doing that first we should go for blunder test, or we have to find out whether any blunder is present in the observable or not. That is called blunder test, and that is done by a test called Pope's tau test. Now this is one of the tests, there may be many tests, I mean many software, different types of tests can be done. So I am only telling that blunder test we will be testing whether blunder is available, and that blunder test is being carried out on the residuals of the parameters. We will take care as an input to the blunder test and find out whether any of the residuals is blunder or not. If it is, then corresponding to that residual we have to find out which one is the observable, and that observable has to be taken out from our observables, and we should go for again blunder test, and again we have to see whether our observables are free from any blunder or not. So this thing has to be iterated till all the blunders from all the observables are taken off. Once the blunder test has been successfully done, that means tau test has been successfully passed, then we should go for residual tests or residual adjustment. Now that is done by chi-square test. Residual adjustment is done by using a method called least square analysis. Through least square analysis all the residuals get adjusted, and then we should carry out chi-square test whether our distribution of residuals are satisfying the criteria that is to be observed for our adjustment or not. Now once till it pass we should continuously carry out, and till it as it passed then we should go for the third test, that is error ellipse. We have to find out the error ellipse are in position of all the control points, that means the location plus minus sigma. This is the error ellipse, and we have to see whether these errors are within the specification, desired specification or not. If it is not, then again we have to go for improvement in data, and in worst case we have to go back to the field, take the new data, and we have to do all these steps again and till we find our position satisfy the error, permissible error. So in this way minimally constrained adjustment, through minimally constrained adjustment we get the position of the relative location of the stations within the desired specification. Now as the minimally constant has been done or completed, then we go for constraint adjustment. Now in case of constraint adjustment, apart from the stations which we observe, we need to have some more stations whose position is already known or whose position with respect to some reference system are already available with us. Sometimes many of these station, one of these station or two of these station, because sometimes we observe this, we take observations from in n numbers of maybe 5, maybe 10, maybe 15. So out of those huge number of stations, sometimes we take observation at some stations whose position is already known with respect to some reference frame. So now those stations, suppose I have taken, we have some station like this. So we have taken like this, suppose of this is the station, whose, and suppose this is the station, these two station already control points is location with reference to some reference frame is already known. So in constraint adjustment we will take these two station location as the known points, and with reference to these we will try to find out the location of all other stations, and we will go for all those adjustments which we had done in minimally constraint and find out whether there is any blunder available or not, and whether these conditions of error ellipse satisfy or not. So till we have to go on doing it till these conditions are being satisfied, that means error ellipse condition is being satisfied. Now after we complete this constraint adjustment, then we go for one more thing, that is called control tie analysis. So in control tie analysis what we do take some local reference station or a station, or in to control tie means we will tie with the reference system in which we want to have our coordinates. So the reference system in which we want to get our location, we need to have some stations in that reference system, and then with reference to that station we will go for minimally const adjustment to that, and we will tie our station to that reference system. So that is called control tie analysis, and in after doing that we will get the location of the stations in the reference system which we are looking for, and the locations which will satisfy the requirement of our specification. So ultimately the output of the network analysis is being achieved. So now here you can see I had whatever we have discussed till now, that has been given through this flow chart, and you can see here that the network analysis starts with the reduced baseline and data satisfying the acceptable criteria of network adjustment. With that data it starts, and then preliminary analysis which consists of network connectivity test and loop closure test, and then minimum constraint analysis where, or minimum constraint adjustment where test for blunder, test for residual, test for blunder if it passes, then test for residual, if it passes then error release analysis. Then in some cases the control time analysis can be done after minimal constraint analysis, or in some cases it can also be done after the fully constraint analysis. So, fully constraint analysis or constraint analysis is same or another adjustment. So, here you see that error elapse analysis we do and it satisfy, then the adjusted position of the point has been arrived. So, with this I want to conclude about the network analysis. This is in short I had given, and anybody want to study in detail, you may study the book, and some review questions are given which you can prepare yourself. And to summarize today's class, network associates with proper improper mutual orientation, wrong scaling factor, misrepresentation of the geospatial location with respect to reference coordinate systems as discrepancies. Discrepancies are due to the presence of residual error resulting in misclosure in the network. So, network adjustment involves testing and removal of blunders, distribution of random error as well as computation of final coordinates. Network adjustment consists of preliminary analysis, adjustment consisting of minimally constraint and constraint analysis and statistical analysis. In preliminary analysis we determine the stability of the network, connectivity and loop closure test. In minimally constraint adjustment, any one of the station held fixed during processing. In constraint adjustment, a priori coordinates of a control point is being considered or held fixed, and statistical analysis is being carried out through tau test and chi-square test, and finally control time analysis is being conducted to fit the network to local, regional or national control network as desired. With this I want to conclude today's class. Next class will be on quality assessment of GPS surveying. Thank you.